In this video, we'll explore linear functions. Now, a linear function is a function of the form f of x equals mx plus b, which looks very much like the equation of a line in slope-intercept form. One thing we do talk about when we talk about slope is that in a function we label it as the constant average rate of change. It's the average rate of change, and that value is constant no matter where you go through the function. So that is just another name you will see for it. When we talk about whether it's increasing, decreasing, or constant, it's all based upon that slope. A positive slope means our function is always increasing. Negative slope, our function is always decreasing. And if it's constant, we have a slope of 0. So here are three different examples, and we'll say, are they linear functions? Well, the first one, f of x equals mx plus b. That's a line, and it's a function. So yes, that is a linear function. Second one, what we have here, since we have an ordered pair of some function that is created, and we want to say, well, is this following a linear function? We want to look and say, well, what's that rate of change, i.e., what's the slope, and is it consistent among all the points? Well, if we look, we're always increasing by 1 for our x values, and we're increasing by 2 for all our y values. So from any 2 points, if we go consecutively here, it's always a ratio of 2 to 1, 2 to 1, 2 to 1. So our slope would be a slope of 2. Since it's the same for between every point, yes, this is a function. The last one here, if we look at this graph, we see that that's a parabola. A parabola follows a quadratic, so no, this would not be a linear function. Now say I want to start with f of x equals 1/3 x minus 2. And I want to know what's the average rate of change. We just have to remember that just means what's the slope. And our slope in this case is 1/3. If they ask for the y-intercept, remember that this is in y equals mx plus b, slope-intercept form. So our b value represents our y-intercept. In this case it's -2. So our y-intercept would be 0, -2. And then is the graph increasing, decreasing, or constant? Well, we look at the slope. The slope is positive, so this graph is always increasing from -infinity to infinity. And last thing, say I could want to find a specific value, f of x, or f of 9. I plug 9 in for x, and then simplify. 1/3 of 9 is 3, 3 minus 2 is 1, so f of 9 is 1. Now I can also use it to model real-world situations. For example, a car rental's charge can be modeled by this function where the cost of x equals 20 hundredths x plus 12. Or it's 20 cents per mile driven. So say I want to know, well, what would be the cost after 120 miles? Well, I'm looking then at c of 120. I'm plugging 120 in for x and simplifying. And then 24 plus 12 gives me $36. So it cost me $36 to drive 120 miles. Now, how far could I go with $100 being the final cost? Well, that means I'm looking at the cost at some certain mileage being $100. So this time I'd be 100 equals 2/10 x plus 12. Subtract the 12, divide by 2/10, and you get that you could go about 440 miles for $100. And then what would be the implied domain? So while the domain of this function is all real numbers, the one thing we pay attention to the fact though is that we're dealing with a situation. We can't have a negative mileage. So our time and our cost actually start at mile 0 once you actually agree to pick up the car. So for that reason, while the function as a general theoretical function is all real numbers, in the case of this problem, it starts at 0 and can technically go on for infinity. So we would write that with the bracket of 0, comma, infinity if we were using interval notation.